Welcome back. In this session, we will discuss about the method of consistent deformations. Method of consistent deformation is a classical example for force method or compatibility method or flexibility coefficient method. Next steps in method of consistent deformation. I said already, this is a classical example of force method, so steps are almost similar to force method. Consider simply a continuous beam ABC. We need to analyze this beam. Analyze means we want to find out the unknown forces. So we are using this force method. First step will be find the static indeterminacy. Here horizontal forces are absent, so we are considering only vertical reaction, vertical equilibrium equation and moment only. We are not considering horizontal equilibrium equation. So degree of static indeterminacy will be r minus 2. Number of reactions will be 1, 2, 3. So it is r minus 2 equal to 3 minus 2 equal to 1. Now choose this reaction RB as the redundant. Now draw the deflected shape of the release structure with actual loads. We are removing this redundant force and we are drawing the actual structure with external loads. Then if there is no support means there will be a deflection in the downward direction for this point B. Let the deflection at B will be capital delta B. Now find the deflection of the release structure due to axial loads at the point of redundancy by unit load method. We should find delta B using unit load method. Unit load method means you will apply a unit load at the point B. We will apply only this load. There won't be any external loads. Then using the relation integral mm dx by a, we'll find we'll get the value minus 5 WL raised to 4 by 384 a as the capital delta V. Negative sign indicates that the deflection is in the downward direction. Now draw the deflected shape of the release structure due to redundant force applied as load. Now we are again drawing the release structure, and if we are applying this redundant load, okay, we are applying this redundant load. Now there will be some deflection delta B dash. To find out that deflection delta B dash, first you will apply unit load at the point B, and you will find out the deflection due to this unit load. You will get small delta B. Now if the deflection due to 1 kilonewton load is small delta V, then deflection due to RB kilonewton load will be RB into delta B. So this will be equal to, no, this value will be equal to delta B dash will be equal to RB into delta V. Now write the compatibility equation for the structure. Compatibility equation means equations involving deflection or slope. Okay, compatibility equation for this structure will be at the support B, at the point B. Okay, there is a roller support, so the net deflection at B in the downward direction will be 0. Okay, delta will be 0. So this downward delta B, capital delta B, should be equal to this upward delta B. Okay, or this algebraic sum of this two will be equal to 0. That is capital delta V plus this is delta V dash will be equal to 0. From this relation you will get the value of RB. RB equal to 5 by 8. Now once we got the value of RB, we can find out RA and RC from the equilibrium equations. And we can draw the shear force diagram and bending moment diagram for the structure. Please note that direction of unit load is assumed positive. This is the sign convention for consistent deformation method, direction of unit load is assumed positive. If you are applying unit load in the downward direction, then that direction is positive. Downward direction is positive. If you are applying unit load in the upward direction, then upward direction is positive. Coming to this example, analyze the beam using consistent deformation method. This is a continuous beam. Static interference equal to 1. Support reactions are VA, VB and VC. Choose VB as redundant. Let VB be the redundant. Okay. Now draw the release structure. Release structure means we are not drawing redundant force RB. We will draw the released structure with the actual loads. Now, if there is no support at B, or if you are removing this VB, there will be a deflection of delta B, capital delta B at the point B. To find out delta B for the released structure using unit load method, we will use unit load method to find out delta B. Unit load method means we will apply a unit load at B. Then using the relation integral mm dx by EI, using this table you will get unit load method values. Using this relation integral mm dx by EI, we will get the value of delta B. Here capital M means moment at different segments due to external load. This is external load. And small m is moment at different segments due to unit load. Now you'll get the value of 73.33 divided by A in the downward direction. This is positive, so this is in the downward direction. Now we should draw a figure of the actual structure without external load. We are drawing only with, if this is point B, we should draw the figure with redundant force only. Redundant force only. Okay. This is 4 meters. This is 4 meters. Then there will be some deflection of, there will be some deflection value. Okay. Okay, say delta B dash. We should find out this deflection delta B dash. And to find out that deflection delta B dash, first we will apply only 1 kilonewton load. Okay. Then we will find out the deflection delta B. Say if the unit load is applied in the downward direction, then we will get some deflection delta B. Now we will find out the deflection due to this point load only. Okay, using the relation integral mm dx by EI. Here only small m is coming because external load is 1 kilonewton, unit load is also 1 kilonewton, so integral mm dx by EI. We can use this table. We can use this table values, okay, for small m values. Okay, from this relation mm dx by EI, we'll get small delta B. Small delta B is due to 1 kilonewton load only. Now we know that delta B dash, delta B dash, delta B dash is the deflection due to redundant force only. Redundant force will be, if this VB equal to VB into small delta B. Okay, this small delta B is deflection due to unit load, 1 kilonewton load. Okay, now we want to find out deflection due to VB, that is VB into delta B. That is, if the deflection due to 1 kilonewton load is 2 mm, 1 kilonewton load is 2 mm. Then what will be the deflection due to 6 kilonewton load? That will be 6 into 2 mm, right? Like that. If the deflection due to unit load is small delta b, then deflection due to Vb will be Vb into small delta b, that is Vb, delta b dash. Okay. Now compatibility equation is this: capital delta b plus delta b dash, that is Vb into small delta b equal to 0. We know the value of capital delta b, we know the value of small delta b. Now get the value of Vb. Vb equal to minus 6.875 kilonewton. This minus sign indicates that the direction of this Vb is in the opposite direction of unit load. That is, we already applied unit load in the downward direction. Okay, so negative sign means this is in the opposite direction. See, Vc is in the upward direction. Sorry, Vb is in the upward direction. Okay, not Vc, Vb is in the upward direction. Now find all other reactions using equilibrium equations. We got the value of Vb as 6.875. Now from the equilibrium equations, we find out Va. Similarly, find out Vc. Draw the bending moment diagram also. Now second example, analyze the beam. Support A is fixed and support B is there, hinged. Static indeterminacy equal to 1. Now reactions are: moment will be there at A, vertical reaction will be there at B, at A, then there is a vertical reaction of P at B. Okay, we are neglecting horizontal reactions here because there is no horizontal load. 3 forces are there, only 2 equilibrium equations, so 3 minus 2, we will get 1 as static indeterminacy. Applied load is P. Now choose Vb as redundant. So we removed Vb. Now draw the release structure with the applied loads. Okay, find out delta B. Delta B means deflection at, this is delta B. Deflection at delta B. Deflection at B. This is B. Using unit load method, we'll get minus 5 PLQ by 48A. Now apply unit load on released structure corresponding to Vb and find the deflection at B, small delta B. Apply unit load in, if we are applying unit load in the upward direction, you'll get this value using unit load method. Now write the compatibility equation. This is the compatibility equation. We'll get the value of Vb. Vb is positive, that is we applied a unit load in the upward direction. Vb is positive means Vb is also in the upward direction. Now find out other reactions using equilibrium equations. Draw bending moment diagram. Now coming to this frame problem, analyze the frame using method of consistent deformation. This is a frame ABCD. Applied load 10 kilonewton in the towards the left at the point B. Flexural rigidity EA is a constant. Reactions are: moment will be there at D, horizontal reaction will be there, vertical reaction will be there, and one horizontal reaction will be there at A. See, the roller is in this direction, so horizontal reaction will be in this direction. Horizontal reaction for a roller support is horizontal to the perpendicular to the plane of rolling. This is the plane of rolling, so in this direction. Okay, so HA will be there, VD will be there, HD will be there, MD will be there. Static interference will be 1. Total number of equilibrium equations 3. Total number of reactions 4. 4 minus 3. Here we will consider all the 3 equilibrium equations because horizontal reaction is present. 4 minus 3 equal to 1. Choose HA as redundant. That is, let HA be the redundant. Now we should find out capital delta HA. Delta HA means at point A, deflection in the horizontal direction. At point A, deflection in the horizontal direction. That is capital delta H. Now small dha. Small delta HA means deflection in the horizontal direction using unit load method. Unit load due to unit load. We can find out capital delta H and small delta HA using unit load method from the same table. Okay, draw the table segment origin limit capital M, this small m. This capital M is due to this load 10 kilonewton. Okay, and small m is due to this 1 kilonewton load. It means unit load. You'll get the value of delta HA like this, not the negative sign. You'll get the value of small delta HA also. Now write the compatibility equation. There is a support at A, so there is no horizontal movement. Okay, the roller is in this direction, so there is no horizontal movement, so the compatibility equation will be net deflection equal to 0. Okay, so the capital delta HA plus HA into this value. HA into small delta HA is the deflection due to HA. Okay, delta HA is the deflection due to 1 kilonewton load. HA into delta HA is the deflection due to HA. We'll get the value of HA equal to 4.423 kilonewton. Okay, draw the BMD of the structure. Now next problem, analyze the frame. Note that here moment of inertia is 2I for this beam DC and for this column CA. This is I. Note the change. Find out the static indeterminacy. You will get the static indeterminacy as 1. Choose HA as the redundant. Find out capital delta H and small delta H using unit load method. We are removing the HA and draw the released structure. Okay. In this problem, if E and I values are like this, and also draw the released structure with redundant load only. We are removing external load only, redundant force is applying. Now tabulate the result and using unit load method find out the value of capital delta HA and small delta HA. And like in the previous problem, we can write compatibility equation. Note that here we'll use 2EI because it is 2I for DC. Moment of inertia is 2I for DC. From the compatibility equation, we will get the value of HA. Now we can draw the value. We can find out the other reactions from the equilibrium equations and draw the BMD. Now analyze the beam using consistent deformation method. Supports are supports are at A, B, C, D. Here static indeterminacy is 2, means 1, 2, 3, 4. We have 4 reactions. So R is 4 minus here only vertical loads are acting. So we are neglecting horizontal equilibrium equation. So 4 minus 2. Equilibrium equations will be static indeterminacy is 2. Okay, we can choose VB and VC as the redundants. Now draw the released structure. That is, draw the structure without VB and VC. Okay. Find out there will be deflection at B, delta B, and deflection at C, delta C. This is the deflection of the released structure due to external loads. Now find out delta, capital delta B and capital delta C from the unit load method. We'll get the values from the unit load method. Now find the deflection at B and C due to the redundant force using unit load method. Now we'll draw the given structure. Now if you are applying 1 kilonewton at B, point B only, there will be deflection at B, that is delta, small letter delta BB, that is deflection at B due to load at B. And there is also a deflection of at C, that is deflection at C will be delta CB, that is deflection at C due to load at B. Like that, this is deflection at C due to unit load at B, and this is deflection at B due to unit load at B. Now again draw the structure. This is B. Now this is C. Apply unit load at C only. C only. Okay. Then there will be a deflection. And now deflection at C is delta CC. Deflection at C. C is delta CC. That is deflection at C due to load at C. This is delta CC. Small letter delta CC. Now there is a deflection of delta BC due to unit load at C only. Okay, this is delta BC means deflection at B due to unit load at C. Okay, now find all these values using unit load method. You'll get the values using unit load method. Now we will be having two compatibility equations because the static indeterminacy is 2. So there is two unknown forces VB and VC. So there is two compatibility equation. Compatibility equation at B is net deflection at B is 0. That is delta B plus, that is delta B plus, delta B means this delta B plus VB into delta BB. VB into delta BB means deflection at B due to this load VB. Okay, that is for this structure we are considering VB and VC. Okay, VB and VC are the redundants, so there is VB and C. I will again draw. This is the applied load. This is the structure. This is VB and this is VC. Okay, now VB into delta BB means deflection at B due to this VB, and VC into delta BC means deflection at B due to BC. Note that this is not a delta CC, this is delta BC. Okay, we are finding out the compatibility equation at B, that is, so we'll use small letter delta BC. Okay, now compatibility equation at C will be capital delta C plus load at C, that is VC, into deflection at C due to unit load at C, that is delta CC, plus there is a load at B also, VB, into we are finding the compatibility equation at C, so deflection at C due to we are this is VB, so due to this B, okay, equal to 0. Two compatibility conditions are there, so solve these two compatibility equations. You'll get the value of VB and VC. Other reactions can be find out using equilibrium equations and draw the SFD and BMD. Now if there is support settlement, for the previous problem, if there is a support settlement means then combat, if there is no support settlement means net deflection equal to 0. So the compatibility equation at B means this is for support settlement only, previous problem is over. So if there is no support settlement, then delta B plus this value will be equal to 0. Then if the support B settles by 5 mm, then net settlement will be equal to 5 mm. Okay, now the problem can be solved as usual. Now find the member forces in the truss using the method of consistent deformation. This is a truss member A, B, C, D. First step is external static interference. External static interference will be 0. Find out internal static interference. Internal static interference is 1. Now choose the member AC as redundant. Say this AC. This is internally static indeterminate. So one member is extra. So let the member AC be the redundant. So we are removing AC. So we are drawing release structure with the actual loads only. Due to the absence of member AC, joints A and C have a relative displacement. So if there is no AC means if you are applying load, there will be some moment of relative moment of this point A and C. Okay. Using unit load method, this relative displacement delta AC will be equal to sigma PKL by A. Unit load method for a truss member is sigma PKL by A. So find out this delta AC from the unit load method. Now we are drawing the released structure with unit load only. Okay, that is in this member only, AC. Now find the displacement the released structure due to redundant force. Okay, you want to find out the released displacement the released structure due to redundant force. So do that. For that you will assume a unit force corresponding to a member AC. Okay. Now find out small delta AC. You will get from the relations KKL by A. Here P and K, external load P equal to K, 1 kilonewton only. So you will use the term KKL by A. Okay. That is, there is no external load. Our load is 1 kilonewton only. Okay. So from this relation you will get the value of small letter delta AC. Now the compatibility equation is, since the net relative displacement between A and C is 0. So actually there is a member AC. So net relative displacement will be 0. So net relative displacement is 0. So the compatibility equation is delta AC. Delta AC means deflection without AC plus FAC into delta AC means deflection due to this force FAC equal to 0. Tabulate the results, you will get these values. Now find the member force in other members using method of joints. So if you know the value of this force AC, we can find out all other members using method of joints. Means if you know the value of AC means this is not a statically indeterminate truss. Not indeterminate means this is a determinate truss. So we can find out all the member forces using method of joints. So member force will be like this. Now temperature effect. Now if this truss member AC, okay, the length of this member AC changes due to temperature effect. Let if the member AC has a initial deformation of 3 mm due to temperature change. Okay. Then net compatibility equation is net deflection not equal to 0. If there is no temperature effect means net deflection equal to 0. Now if there is a change in dimension or there is a net movement of 3 mm means net deflection equal to 3 mm. Okay, so compatibility equation will be delta plus T into delta, or deflection due to this force equal to 3 mm. Okay, net deflection equal to 3 mm. So if there is temperature change and change in dimension, then net deflection is 3 mm, and if there is no temperature change means net deflection is 0. Thank you.